Hello everyone, I'm Yiyue from MIT, and I would like to present our work on digital fabrication of pneumatic actuators with integrated sensing by digital machine knitting. Pneumatic actuators have shown enormous promise in applications such as soft robotics, assistive wearables, and interactive devices due to their low response time and relatively large output power density. Over the last decade, researchers demonstrated diverse soft silicone-based pneumatic actuators designs by molding, which is one of the most common techniques for pneumatic actuators. Recently, textiles and fabrics have been devoted as candidates for soft actuators thanks to their ubiquitous utilization in everyday life, high strength-to-weight ratio, and compliance with the human body. Researchers have demonstrated textile-based pneumatic actuators through intrinsic modifications or extrinsic reinforcement of the textiles. These strategies, while effective and now in widespread use, are both manual and require trial and error cycles to optimize designs. Further, incorporating sensorization into such workflows is rarely considered, and simple, established recipes for doing so are lacking. To overcome the shortcomings of current workflows, we propose a method for rapidly fabricating machine-knitted, customizable pneumatic actuators with integrating sensing, and offer a predictive simulation and interactive graphical user interface for users to design and preview actuator behaviors easily. Here shows an overview of our typical machine-knitted sensorized actuator with one actuation region, 3 resistive pressure sensor, and 2 swept frequency capacitive sensors. Our actuator is composed of 2 parts, an off-the-shelf thin-wall silicone tube, which serves as the base pneumatic channel, and a knitted sheath with programmed stitches, which wraps over the silicone tube and confines the shape of the inflated actuator. The deformation of the actuators is mainly defined by the knitted sheath with locally variable extensibility. As an example, here the front of the tubular knit is constructed with normal acrylic knitting yarn, and the back of the tubular knit is constructed with mixture of normal knitting yarn and elastic yarn, which is about 100 times more extensible than the normal knitting yarn. We then wrap the knitted sheath over the silicone tube and anchor both ends of the wrap tubes by clamps. When the silicone tube is inflated, the elastic stitches at the back side of the tube tend to extend more than the non-elastic stitches, which forces the tube to bend forward. We also integrated 2 different types of sensors into our actuators. The integration was done automatically through one single knitting machine run. We leveraged the plating technique to insert conductive yarns at specific locations, where the conductive yarns are blended with the normal knitting yarn. The knitted conductive yarn loops interlock loosely when there is no external pressure. When applying a load, the conductive loops collapse, resulting in more electrical path and therefore the resistance drop. It is worth mentioning that we apply a few knitting tricks to prevent the pressure sensors from being stretched when the actuator inflates and ensures the reliability of the pressure sensor performance. Details can be found in our paper. We also integrate capacitive sensors. Swept frequency capacitive sensing leverages the fact that alternating current signals of different frequencies flow through different paths at the capacitive interface between the electrode and the body contacted objects. We integrated conductive yarns at specific locations on the knitting actuators as the capacitive sensing electrode. And by collecting amplitude response over a range of frequencies, we retrieve information on the existence of human touch or human contacted objects. To allow users to design and preview inflated actuators quickly, we provide an interactive design system and a predictive model by which users are free to specify the actuation regions and sensor locations, preview the actuator's shape, and export low-level knitting machine instructions for immediate fabrication. We incorporate a predictive simulation model in our user interface, which allow users to preview the inflated shape of the designed actuator. To obtain a realistic simulation result, we use a data-driven strategy to capture the shape of individual normal and elastic stitch faces under pressure. Details can be found in our paper. Here shows the qualitative results of our predictive simulation on a J and S-shape actuator. We further conducted a user study to evaluate the usability and effectiveness of our computational design interface. During the study, we asked the participants to perform two tasks without and with the simulator feedback. The first task asked user to design an actuator such that the endpoint of the actuator would make contact with the specific location when inflated. The second task asked user to design an actuator that can circumnavigate a specified cylinder while hitting the target when inflated. Here are some simulated and fabricated example designs, which users design using our user interface. In general, participants achieve higher accuracy in both tasks, consider the task easier, and obtain more confidence in their designs when our predictive simulation tool was provided. Such results indicate the usability and effectiveness of our design pipeline. Finally, we demonstrate diverse application scenarios of our machine-knitted pneumatic actuators. Our actuators have outsized potential as assistive wearable solutions because they are low-cost, lightweight, breathable, conformal to human body, and compatible with the current garment manufacturing process. Here, we seamlessly integrate our actuator into knitted garments, such as glove and sleeve. They were fabricated in one machine run as a whole piece of garments. Minimal muscle activities are obtained when completing tasks and motions when using the assistive glove and assistive sleeve. We design and fabricate a soft hand with 6 individual machine-knitted actuators. By activating different sets of actuators, we can perform diverse grasp on objects of various sizes, geometries, weights, from a tennis ball to a wooden block in a reliable manner. We demonstrate a 2-finger gripper with integrated pressure sensors and sweat frequency capacitive sensors. The amplitude response from sweat frequency capacitive sensors offer a real-time feedback on the presence of objects along the finger interior, while the integrated pressure sensors provide real-time feedback on the quality of the grasp. Our machine-knitted actuators with integrated sweat frequency capacitive sensing can be used as an interactive robot. We assemble 4 separate actuators, each integrated with an electrode for the sweat frequency capacitive sensing. Real-time sensing feedback allows the robot to respond interactively. When a human's touch is detected, they either activate or deactivate. Our actuators can further be arranged as legs for soft quadrupedal robots. Each of the 4 legs consists of 3 actuators, 2 of which bend forward and backward, while the third one bends the leg upward vertically. We predefine the motion pattern of each leg, combined to form a rowing-like motion. The quadrupedal robot can locomote forward and backward by actuating all legs with the same sequence. It can be also achieve a turning motion by actuating the legs on one side forward and the other side backward. Thanks for listening. More details can be found in our paper.